But now it's my pleasure to present the work that I do together with my PhD student, Tariq Mohammed Nasir. So we are also working on program repair. And maybe before I start, can answer your question. I try to answer it. So at the moment, these tools, they can only fix really simple bugs. But you know, it's gradually, we work on improving it. But many of them, as my colleague before said, they propose a fix and they run a test suite. And if the tests pass, it's a candidate fix. Then still the developer, of course, needs to evaluate it. So that's the good thing, not to make developers obsolete. That's far away, I think. But still, they recommend lots of, let's say, patches that the developer would say, I will not accept. So that's it. So we work on sound automatic repair using symbolic execution. Okay, let's jump into it. Yeah, we heard developers spend lots of time fixing bugs, 90% understanding it, then fixing it, testing it, and then so on. So it's quite a lot of time. Whether the number 90% is correct, I don't know, but it's really a high ratio or a high percentage that developers spend. And that was, I think, one of the main motivations of researchers to jump in and say, okay, if we can reduce this time by a little bit, it basically benefits the developers so they can spend time on fixing the more complicated bugs. Okay, so they proposed several approaches during the last 10, 15 years. So it became auto repair. It became very popular. It started with genetic programming. Basically, okay, they modify the program, single statements, step by step, and after each modification, they run the test suite and check, okay, is this, does it pass or not? If it passes, it's a candidate fix. Then you already see that can take quite a long time because it can propose how many different ways of modifying let's say a medium or a small size of a small size program. So you really run very fast in, let's say, an explosion program, combinatorial explosion program, because you can modify it in many ways. Then other approaches have been proposed, and the one we were really, it's here, so it should also, we were basing on was this extract fix. Why? Because it's not doing this test suite based program repair, but it uses symbolic execution, and then also and it's checking then whether the batch really satisfies a constraint, giving all possible inputs. And that's not just running 5 tests, and if it passes, it can be accepted. Okay, drawbacks. Yeah, the first one I already said. Many suffer from overfitting. Overfitting means they generate the batch, they modify the code in a way so that it fits the test suite, so that the test suite passes. Then constraint-based automatic repair. They try to address overfitting, so it's not 2 or 3 years old, that approach. But they still need a test case to trigger the bug. So they use a sanitizer to instrument the code, then they need a test case to trigger that bug, and then they output the constraint for generating the batches. So because it's a constraint, also the quality of the generated batches output by extract fix is still questionable. I will give them an example. So the example is here. So for instance, here it looks a bit messy, yeah. But at the end, it's basically here for main, you allocate a buffer, static size 5. You assign the input from the command line, of course, if it's longer, and then you copy that input into the buffer. If the input from the command line is longer than 5 bytes, point out of bounds. Yeah. Right? Should be caught by existing bug detection tools. And yeah, and the batch that it generates is then here. Basically, what extract fix is doing is, okay, it finds, here, okay, there is the crash location when you do the assignments, and the pointer runs out of bound. He figures out, okay, I needs to be lower than the global size MS heap, which is a bit of a cryptic name they use from the sanitizer, which here is set to size, and size is 5. Okay, so it's 5. And what they do then is they propose, okay, to fix it by replacing that for loop statement, the condition in the for loop, just by adding that constraint. So I needs not only to be less than size of the content of the input, but it also needs to be lower than the size of the buffer, which is here stored in the size is stored in this no global MS heap overflow, which is 5. Would the developer fix it like this? Just. I also don't think he would do that. It's safe, so now it runs, but it basically, it changes the behavior of the program, because actually, I guess what the developer wanted is reads or copy the input into the buffer and then do something with it. But don't cut the input and just copy the first 5 bytes out of it. So maybe a better patch could be that you say, instead of allocating 5 bytes, first read the input, then check how long is the input, and then allocate enough bytes for it to store it. Maybe a better patch. But at the moment, honestly, I don't know any program repair tool that can suggest such a or output such a patch. Maybe there are, let me know, but we didn't find one. Okay. Then, so now we thought we had one idea. There's symbolic execution. Also, SymDefFix is only running, needs one test case, so it has one error path. It uses a sanitizer to output that information from one error path. So maybe when, so that means when the error is hit in the code, it outputs, it has all the state information from that error path, and that it outputs. We assume that with symbolic execution, where we can explore multiple paths and also multiple potential error paths, that we have more information about that error then. And if we have more information about that error, we hopefully can also create better patches. And so this is one step, and the other step is, of course, then also in the patch synthesis, which is future work. Yeah. Now, symbolic execution, that is the first step we are still working on. So we have some preliminary results on that. But okay, what we wanted to do is we wanted to modify SymDefFix, replacing that execution of a test case by symbolic execution, and output that's then this crash constraint that is violated at the bug location, also using symbolic execution. So can we get that information out of KLEE that we use? Okay. So we modified KLEE a bit, but there was a little bit more work to do. So we wanted to combine it, or we combined it with SymDefFix. We wanted to still keep the parts of SymDefFix that then actually generated the patch. This is the future work to do to also improve that. At the moment, it was, can we replace the first part of SymDefFix, meaning the sanitizer plus the test case, by symbolic execution? What we used, we still needed to use some part of SymDefFix to instrument the code, so that we could get this this variable or information about the memory, about the variables that are needed by SymDefFix later on, to generate the patch. So we used that instrumenter. Then we used, then we used Symbiotic, because Symbiotic made it a bit easier for us so we didn't need to write the test driver. That was fine. So we focused on MEM safety bugs at the moment, and we checked their SD comp. We checked who were the, let's say, the most successful tools there, and Symbiotic was one of them. And Symbiotic also used is based on symbolic execution. So we used that, and inside their Symbiotic, there's the KLEE engine, check KLEE now, to detect a bug, and then we had to modify. So the green part here is where we added our modifications. So basically we extended the KLEE engine there, basically the executor class, to output that information. One information is to get the crash-free constraint. So when the symbolic executor or interpreter hits the bug, so that we can get that violation. And we also track the call stack until then. Okay, so instead of doing it statically, yeah, we do it now using symbolic execution. As I told you, yeah, we modified the terminate state on error method. And then the second one with the, what was it? We modified also the execute instruction method. And here the constraint that we need to output is basically where does it happen, in which file, in which method, which line of code, and what's the constraint that is violated. Yeah, violation here is the error that I needs to be less than global MS heap overflow. And with that, basically this input is needed together with the call trace, so the interprocedural call trace, when in which method does the bug occur, is fed into SymDefFix so that it then can continue with finding the fixed locations and then generating the patches for each fixed location that it finds. So we were successful in implementing that stuff. So we had to deal with, we were not so much into KLEE. Now we are a bit deeper into it, but still not deep enough, as I found out. We succeeded in that we could at least output the same batch as SymDefFix did, but now just using symbolic execution. It's a small step, but it's a step where we want to continue. So that's from now on, we hopefully can exploit or leverage the information that we get from KLEE, and not only for executing one test case. And where this will lead us, we will see hopefully that we can use that information to then create better patches. And that's it. So that's the current state. Future work, yeah, we still need to consider all error paths. The moment we just output one, because we started a lot with integrating the tools, symbiotic with SymDefFix and so on. Next step is also improve the algorithms to determine the fixed locations, and then especially also the synthesis of the batches that should leverage that information from the symbolic execution. Yes, so that's it. That's what Dalek should have told you or presented to you. I'm happy to welcome your questions.